Hi, my name is Brandon Sandoval.
Hi, I'm Zachary Walker.
And today we're going to talk to you about polymer membranes. Now, if you're like Dylan right here, you might be thinking, what's a polymer? So quite simply, a polymer is a large unit of the same individual units interconnected together. So right now, we don't have a polymer.
I am a unit.
I'm a unit.
I also am a unit.
I'm a unit.
Now, when we put these units together, we're going to get what you see as a polymer. So this would be like a people polymer.
Now that we know what a polymer is, we're going to move on to the next section, which is to define a polymer membrane. The reason a polymer makes such a good membrane is that it allows certain things to go through, such as small molecules, whereas it'll stop bigger molecules from moving through. Some big molecules may go through, but others may actually get stopped on the membrane due to the permeability of it.
So three very important characteristics of a polymer membrane are free volume, solvent diffusion, and permeability. Now, Zach talked a little bit about permeability, and permeability is defined as the state of the membrane which allows certain fluids to go through. So whenever we look at the state of this membrane, it has a very high permeability for the low molecules as they go through relatively easily, whereas they have a low permeability for these larger molecules as they won't go through.
Now moving on to solvent diffusion. Solvent is defined, in this case, as the air on this side of the membrane on the other side of the membrane. Now, if we were to treat this as the molecule that's going to be moving through the membrane, or passing through it, or even, in this case, diffusing through it, some of the air will travel to the other side, which is known as solvent diffusion.
So the last characteristic we're going to talk about is free volume. Free volume is defined as the space in between molecules. So when we look at the polymer right now, there's not a lot of free volume in between them, which makes permeability of the molecules very hard. Now, if we look at the polymer now, there's a lot more free volume, so this permeability increases, which allows the molecule to go through. The large ones are still going to have a tough time going through. So now that you know the basics for polymer membranes, we're going to talk you through a little bit of polymer membrane history. We're going to create a timeline, and as we go through this timeline and add all the different processes, we're going to allude to the three things we talked about: free volume, solvent diffusion, and permeability. So the first process on this timeline is going to be microfiltration. Microfiltration had its start in the 1920s in the laboratory setting. So back in the day, these scientists would want to filter yeast and bacteria out of a lot of aqueous solutions, and microfiltration is how they did it. Now, this drawing right here is a very good example of what a microfiltration membrane would look like. So these right here are going to be the pores, which a relative size for them would be 10 to 0.5 micrometers. So these right here would be the pores that actually decide how much solvent or solute are going to diffuse through. Now, overall, this membrane is going to have a large free volume due to those pores, but outside of those pores, in these areas right here, you're going to want very, very small free volume, just so that nothing that you don't want to diffuses through. And lastly, just for relative terms, we're going to say that these pores are relatively large. So since they are so large, the driving force for this is going to be a very low pressure. You don't really need to do a lot to diffuse your solvent or solute through it. So microfiltration is currently used in industry for sterilization in pharmaceuticals and beverages.
Moving on to ultrafiltration. Ultrafiltration started in the 1930s, with the main difference from microfiltration being the smaller pore size of 0.05 micrometers to 1 nanometer. This smaller pore size means that there's less free volume, which in turn means that if you have a larger molecule on this side, it'll get stopped at the barrier, whereas the smaller molecules will diffuse through the barrier with the solvent. Now, this type of filtration has many applications, ranging from extracting a protein from whey, all the way up to pharmaceuticals and textiles.
The next membrane process on our timeline is going to be hyperfiltration or reverse osmosis. Now, hyperfiltration arose in the 1960s as a cheaper way to desalinate water. Now, back in the day, the most common method for water purification was distillation. Now, distillation required a lot of heat to be inputted into salt water to evaporate the water and thus separating it from the salt. and then you had to cool that water vapor down to return it to its liquid state. Now, as you can see, this requires a lot of energy and therefore costs a lot of money. Now enter hyperfiltration. Hyperfiltration membranes, as you can see, have much smaller pores when compared to that of ultrafiltration and microfiltration. The pores are generally smaller than 2 nanometers, and what this means is that the solvent, or the water in this case, is able to flow much freer than that of the salt. The salt will be retained on this side while the water will flow through. Now, because the pores are so much smaller, that also means that when you compare a hyperfiltration membrane to that of ultra and microfiltration, that the free volume is going to be much smaller. You have a lot less free volume in this membrane, as you can see, compared to those two. The only drawback to having such small pores is that you have a resistance to flow here. So you have to input a lot of pressure so that the flow is able to go freely. Aside from water desalination, hyperfiltration membranes are used for a lot of solvent purification. Now, as you can see, the smaller pores allow for a higher permeability value of the solvent to flow through, whereas the permeability value for the solute would be very small. And this is why they are so common.
Moving up to the 1970s. Now, in the 1970s, we have gas separation. This arose because of the need for be able to separate multiple gases in a cost-efficient manner, as well as in an energy-efficient manner. Originally, we were using cryogenics, but that's very costly, as well as it uses a lot of energy. Now, for the different types of membranes used in gas separation, we have porous and non-porous. Now, other than the pores, the main difference between porous and non-porous is the fact that porous operates under a principle called Knudsen flow, which is where the path length is much larger than the actual pore diameter. Now, this results in low separation with a single membrane. However, if you have multiple cascading membranes, you'll have a higher separation. Moving on to non-porous, however, brings us to 2 more categories. Glassy, which can be defined as a stiff sort of membrane, or rubbery. With glassy membranes, you typically have a high selectivity but a low permeability, and with rubbery, you have a low selectivity and a high permeability. Now, overall, depending on whatever type of membrane it is, usually it'll change the permeability based on what composition of membrane it is. So if you have something like silicone rubber and carbon dioxide, silicone rubber will allow carbon dioxide to move through more readily versus something like PVC or polyvinyl chloride, which allows very little carbon dioxide to move through. Now, economically, porous is very expensive and non-porous is not much better, but they do have their uses. Porous is used mostly for uranium enrichment with very few uses overall, and non-porous is used for hydrogen recovery in numerous processes.
Now, last but not least is prevaporation. Prevaporation arose in the 1980s, and it's a very complex process that involves thermodynamics, heat transfer, and mass transfer. So I understand that these 2 diagrams over here look a little intimidating, but don't worry, I'll walk you through them. So in prevaporation, the membrane is actually used to separate a liquid and a vapor phase in both of these examples. Now, for this process to work, you need your liquid feed to have an atmospheric pressure or larger pressure, and your permeate, or what you're trying to separate, at a much lower vapor pressure. So in an instance like this, you can achieve that 2 ways. You can achieve it by having a carrier gas or by having a vacuum pump. Now, both of these are there to achieve that pressure differential that we want as a driving force for the process. A carrier gas here is a gas that's simply flowing along the process but is not reacting or doing anything much more in the process itself. Now, a common application used for prevaporation is that of the dehydration of alcohols, or the removal of water from alcohol. Now, to better illustrate some of the examples that I'm going to talk to you about, let's take into account an example of separating ethanol and water with the use of a PVA membrane. Now, since prevaporation is a very concentration-driven process, let's take into account an example of a low ethanol concentration and that of a high ethanol concentration. So if we start with a low ethanol concentration, your membrane will actually show almost no selectivity, and the separation be non-existent. However, when we take into account the concentration of ethanol being large, you see that the membrane will actually show very good selectivity for water, and the water will be able to become your permeate by diffusing through the membrane. Now, another thing that you have to take into account for is swollen membranes, and this arises from the example that has a low concentration of ethanol. Now, a swollen membrane typically occurs whenever your solvent diffuses into the free volume of your membrane and just clogs it up and expands the membrane so it just swells it up. Now, because your membrane is being swollen up and being clogged up, there's no space for your permeate to diffuse through the membrane, and thus it becomes a very inefficient process. In order to get around some of those problems, the Flory-Huggins parameters and the theories can be taken into account to match up your membrane with that of your feed and your feed concentration and a lot of other conditions. Aside from the dehydration of alcohols though, pervaporation is also used in food, the pharmaceutical industry, and the chemical process industry. In the chemical process industry, pervaporation is a very attractive option because you're able to get around the problem of an azeotrope point that you would normally find in your distillation process. So an azeotrope is a point where you can no longer separate your liquid mixtures any further, even no matter what you do to your temperature or your pressure, and that's something that isn't faced with these two examples. So now that we've covered a lot of polymer process and polymer membrane history, let's make sure you got it all. We started off in the 1920s with microfiltration, quickly followed by ultrafiltration in the 1930s. Now that was quickly finished up in the 1960s with hyperfiltration. Now as you can see, as we move forward in time, our pore size got smaller and smaller. This was done because we wanted to be more selective with what diffused through the membrane, and as the technology got better, we were able to make these pores smaller so that only certain aspects of your mixture were able to diffuse through it. Now, that's everything, and thank you for sticking with us for Polymer Membrane History 101. Wait a minute, did you forget about gas separation and pervaporation? Because we didn't. These tricky processes started off in the 1970s with gas separation. Now, in gas separation, we talked a lot about porous and non-porous membranes, stiff and rubbery membranes, and how you could pair all of these different types of membranes with gas mixtures to separate them based on what you want as your product. And the final process was pervaporation. Pervaporation was a complex process that involved heat transfer, mass transfer, and thermodynamics. And it would basically take your liquid feed and separate it into a vapor permeate by driving force of a low vapor pressure in your final product. So now that you've seen all of these polymer membrane processes and their history, we hope that your understanding of free volume, solvent diffusion, and permeability that we talked about at the beginning, we're able to show you how these cool processes actually worked and how we're able to use them to get what we want at the final product. Thank you for sticking with us in Polymer Membrane History 101. Now go out there and teach your friends about polymer membranes.
And with a special thanks to Robert E. Keesting and Marcel Mulder to be able to show us all the basics of polymers and to be able to help us illustrate everything that you need to know about polymer membranes.
We would like to take another moment to thank all of our actors from the initial scenes, starring Andreas Olivo as monomer number 1, Aaron Lambert as monomer number 2, Dylan Rathman as monomer number 3, and finally, Dustin Kennefaig as monomer number 4. We did have a guest star of Skylar Mullins as our small molecule propulsion export, or our paper thrower, and Nick Agerter served as the cameraman, which allowed both Zach and I to show you our pretty faces as we explained everything that you needed to know.
This has been a Two Broke College Students production by Zachary Walker and Brandon Sandoval.